In this video, we're going to take a look at regular expressions as an alternative to finite automata for recognizing valid strings in a language. Just a quick reminder of what we've talked about so far. We have introduced the idea of finite automata, both deterministic finite automata and non-deterministic finite automata, as a way of defining regular languages. We use sigma as a notation to indicate the valid characters of the alphabet that would appear in the strings in these languages. So for example, we could say something like sigma is equal to the set of 0 and 1 to represent all bit strings. And then we've had other constants that have appeared in our description of these languages. For example, the empty set here, epsilon to represent the empty string. And then just using the characters that appear in our set as valid characters in our strings, in the strings in our language. Regular expressions are a third alternative, and just another reminder that anything that we can represent with a DFA, we can also represent with an NFA, and vice versa. And this is true with regular expressions as well. Anything that can be represented with a DFA or an NFA, it can be represented with a regular expression and vice versa. So we're talking about three different tools to basically be able to handle the same main task, which is to represent or identify valid strings in a particular language according to whatever rules we've set out. Regular expressions are a compact form as compared to the diagrams that we see with finite automata. So a regular expression is basically formed with the characters of the language along with special operators. There are lots of different operators that can be used, but there are three primary operators that basically can be used to represent any language we like, valid strings in any language we like. These are alternation, concatenation, and the clean star. Alternation basically is this OR bar, this vertical bar that we see, that represents the idea of either or, either one of these choices. So where we see R and S in these descriptions, we would recognize that R and S are themselves regular expressions. So if we want to say something can be one of two possibilities, then we would describe the first possibility and then use the OR bar and then describe the second possibility. Concatenation just says we want to glue these two parts of two regular expressions together, one after the other. So R followed immediately by S says we have this regular expression immediately followed by another regular expression. Again, remember that R and S themselves are regular expressions, so it could be that R has an alternation description, it could be that S has an alternation description, it could be that neither has an alternation description. And then finally, the clean star, which is the little asterisk, superscript asterisk that we see here. This is the idea of identifying 0 or more copies of R. And again, R is a regular expression, so it could be a concatenation repeated multiple times. It could be an alternation repeated multiple times. It could be a combination of all of these things. Alternation, concatenation, and clean star have an order of operations. So the priority is the clean star first, and then concatenation, and then alternation. But we can use brackets in the same way that we can use brackets in arithmetic expressions to reinforce or to enforce a different order of operations. So let's take a look at an example. We looked at this example before when we were looking at finite automata. So here we have a DFA that recognizes non-negative even binary integers. We recognize that a non-negative even binary integer over the alphabet 0, 1 would be any string that ends with a 0, because all even numbers end with a 0. So this is the DFA for that. The regular expression would look something like this. We have a string that is going to end with a 0, and then what comes before that, so here's the concatenation part of it, is any number of zeros and ones. So it could be just a 0 by itself, or it could be a whole bunch of ones and zeros before that 0, but it has to end with a 0, so we see that here. So here we have a combination of alternation where we say it could be either 0 or 1, repeated many times, but it must end with a 0. So we have example here of the clean star, the alternation, and concatenation all at once. Now, if I compare the DFA to the regular expression, it's not obvious that these two things are connected. But I could take another crack at using a finite automata, create a NFA to represent this idea, and now we can start to see stronger connections between these two. It's not that it's always obvious, but oftentimes it's easier to see a connection between a regular expression and an NFA than necessarily with a DFA. So an NFA version of this could look something like this, where we say, okay, we're going to repeat as many times as we want zeros and ones, and then as soon as we see a zero at the end, we're going to recognize that as an even number. Recall that what makes this an NFA is that on a zero, I may stay in the same spot, or I may move to the final state in this case. If I read a zero and it's not the last character in my string, then when I read that zero move into the even spot, I'll end up losing that clone. That clone will die in the evaluation of this expression, of this string. But if we do end up reading a zero at the end of our string, we'll end up with a clone in the final state. So here we can see a stronger connection where we have this idea of the repeated 0 or 1 here in the NFA itself. Let's take a look at another example. Here we have an example of bit strings containing the pattern of 101. And again, we have an NFA to represent this particular string, recognize these valid strings, these strings as being valid. So here we see the NFA says, okay, take as many zeros and ones as you like, and then if you see a 1, start moving closer to the final state. If that's followed by a 0, that's great. If that's followed by a 1, we're in the final state. And then it doesn't matter how many zeros and ones we see after that, but we would stay in the final state at this point. If we saw a 1 and then that was followed by another 1, well, that clone would end up falling off. But we could still have a valid string, because if we see a 1 followed by another 1, we also have a clone in the start state that we're tracing through. How does this look as a regular expression? Well, we see the same kind of idea where we have 0 or 1 repeated multiple times. And then we see the pattern 1, 0, 1. This is a concatenation. And then we see 0, 1 repeated multiple times. Again, oftentimes it's easier to go between a regular expression and an NFA rather than to a DFA. So if you'd started with this idea of representing this idea, or this valid string of zeros and ones that contain the pattern 1, 0, 1, then we could think about, well, let's put the pattern there and that pad either side of that pattern with any number of zeros and ones in our regular expression, and then I could convert that into an NFA. Here's another example where we have bit strings containing either 2 zeros or 2 ones in a row. Again, there's the NFA that represents a valid string, or that would recognize a valid string in this case. And we can take a look at the regular expression that would basically match up with this particular NFA. Again, we have this idea of 0 or 1 repeated as many times. It could be 0 times, but it could be repeated many, many times before the key part of what we want to recognize, which is we see 2 zeros in a row, or we see 2 ones in a row. So now we have a clean star concatenated with an alternation concatenated with another clean star, and each of those clean stars are applied to a concatenation. So again, this idea of the clean star, the alternation, and concatenation being combined in any way we want, each of those, as we're doing that combination, each of those things themselves could be regular expressions, which could be quite complex. So we might ask ourselves, now that we have this idea of regular expressions, why would we ever want to draw something like a DFA or an NFA? Well, there are times when finite automata are much more appropriate for what it is that we're actually trying to represent, especially in design. But there are also times where it's just not obvious what things would look like as a regular expression. If we look at this example of a DFA that recognizes non-negative base 10 integers that are multiples of 3, it's a little bit complex, but it certainly is a manageable idea of creating something that would recognize valid strings in this case. It is, as I said, anything that can be represented with a DFA can also be represented with a regular expression. So it's possible to write a regular expression that recognizes valid strings of according to this rule, but it's not obvious or intuitive how this would be done. So sometimes it's just easier or a better choice to use a finite automata rather than using a regular expression. Having said that, regular expressions can be used in a lot of different situations, not just in computer science or in the scanning process of our compilation execution. So here's a little bit of a cheat sheet in terms of how we would convert something that each of these operators, each of these regular expression operators, into a finite automata. So where we see concatenation, for example, we would just say we would be moving along those characters on transitions from one state to another. So if I have A followed by B, then that would say, well, let's go from one state on an A to a new state, and then on a B to a new state. And if we've reached this Q2 state, it means that we've seen A followed by B. Now this may or may not be a final state at this point. That's going to depend on the particular problem. But this could be progress towards the final state. With alternation, if I see something like A or B, well, normally what that means is I'm going to take this, start from the state, and if I see an A, I'll go in one direction. If I see a B, I'll go in another direction to a new state. And again, this may or may not be a final state. It's going to depend on the particular problem that we're trying to solve. If I see A or B, and then there's something else to be concerned about, then I would add more to my finite automata. With the clean star, if I see a single character repeated, then I'm just going to see a transition back to the same state on that character. If I see something like an alternation, I can go again have a transition back to the same state on either one or as many choices as there may be inside the brackets of the alternation. So in this case, if I have A or B repeated, then I'm going to have a situation where I have a transition back that will go either back on an A or back on a B. Note that this does not mean A is followed by B. So what would be valid here, what would allow me to move forward here would be a whole bunch of B's with no A's at all, or BA, 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 or ABB, ABB. All of those things would keep me in the same state. And then if I saw something like ABC, that pattern repeated with a clean star, then I have a situation like this where I would follow an A to a new state, follow a B to a new state, but C would take me back to where I started from. So here, if I'm in Q0, for example, that I've either seen 0 patterns of A, B, C, or I've seen multiple patterns of ABC, one or more patterns of ABC. That's what gets me back to Q0. Now, with these basic building blocks, you can think to build up a DFA or an NFA that would represent more complex expressions, more complex regular expressions. If you want to, remember with an NFA that you can use lambda transitions to move you from one part of the diagram, one state in the diagram to another state. A lambda transition is something that allows you to move from one state to another without actually reading a character from the input. And that can be quite helpful, especially if you're trying to take a regular expression and convert that regular expression into a finite automata. There are more operators that exist for regular expressions, and there are even more than what are listed here, but I'll just mention a few. Those would be things like square brackets to indicate a range. This is just a shortcut, so I could have written a whole bunch of alternations with an expression. So I could have said A or B or C or D and so on up to Z. But this is a nice clean shortcut to just say, let's talk about a range that's a well-known range. All the letters from lowercase a through lowercase z. I can use a plus sign, which is different from a clean star, except that we don't allow for 0 repetitions of that pattern, of that particular character or pattern. So we would guarantee there's at least one instance of that particular character or pattern. The the reality again here is that it's not necessary to have a plus sign. We can just replicate that idea by just having something like a star, A concatenated with A star to represent the idea of A plus. But it is sometimes nice to have that convenience. We can use a dot to be basically a placeholder for any characters from the alphabet, and so dot at, for example, would match hat or cat or fat or bat and so on. We have question mark, which allows the option of including that character or not. Again, this is a convenience. We could have just as easily done that with an alternation. Now, we also want to be able to include the special characters that we see as operators as regular expressions in our regular expressions. So to do that, we use the backslash character to indicate that we want to include that actual character rather than referring to it as the operator within the regular expression. So there are multiple applications of regular expressions. For example, you could create a scanner, and there are some tools that are standard tools for creating a scanner. Two of these are Lex or Flex. And what scanners need to do is they need to identify what tokens are valid within source code. So things like keywords are really easy to identify because we just type out the keywords exactly as they are. But things like that are dynamic in nature are more difficult, and this is where regular expressions can be quite helpful. If you want to take a look at this on your own, you can go and do some investigation. You can see that the contents of something for a Lex file or a Flex file would include things like regular expressions. So for example, if we wanted to be able to identify floating point numbers, we could write a regular expression like this, where we say you could have an optional plus or minus sign. So I'm going to use the backslash before the plus because I want that actual character to be allowed, and it's optional because I have the question mark here. And then we allow 0 or more copies of the digits from 0 through 9 before a dot or a decimal point. And then following that, we need to have at least one. If we're recognizing this as a floating point number, we would see at least one digit 0 through 9, but we could have many, many digits after the decimal point in this case. So we could have many digits appearing in that case, and we would use a plus in this case, in this situation. There are other places where regular expressions come into play. For example, egrep is a tool that is used in Unix that allows for pattern matching. I'll just do a quick demonstration here. If I wanted to identify, say, from this source code, all of the memory access instructions in this particular program, what I could do is I could just do egrep, where I provide a regular expression, in this case, load word or save word. These are memory access instructions on my in my file print integer.asm. And what it does is it would go through the file that we previously saw and then just do some pattern matching to show me the lines in which that particular pattern appears. So this has been a quick overview of regular expressions as an alternative to finite automata for recognizing valid strings in a language.